Deputy Director of the Infocomm Research Institute, and also runs the telecommunications research in the institute. But she's got also 2 academic appointments, so really straddling again academia and industry. And of course, she's not unknown to this community because she's also a governor of the VT Society. She's a governor of the Communication Society as well, a fellow of the IEEE, and of course, a wonderful fellow to be friendly with. So with this, without any further ado, join me in welcoming Sumei to the platform.
Thank you, Layush, for the nice introduction. And also thank you for giving me this opportunity to speak and also share what we think when we move towards 6G, especially from the industry revolution perspective or the industrial Internet of Things perspective. So before I start the discussion, I would like to have a quick overview on the various megatrends as published by the different analytical firms, such as DNL, GL, and also this Frost and Sullivan, and also like the MIT Sloan Magnificent Review. So if you look at the different trends that have been predicted when we move toward 2030, we see a very nice convergence for the hyperconnectivity and also the artificial intelligence of everything. And then if we go and zoom into a few topics as shown in the Frost and Sullivan's prediction, we can see a few nice converging trends such as Industry 5.0, digital reality as a frontier technology, and also the era of intelligent assistance, Uberization, as we have just heard about, mobility as a service, and also the zero latency world. So with that, how would we actually look at the shift, and also how does it relate to us in the cellular and wireless communications? So we are going to move quickly to the example of the industry transformation. We have spent about the last 15 years for the Industry 4.0 revolution. And for that, we have been making good efforts to converge the physical, digital, and also the virtual environments through the cyber-physical system design and also the industrial IoT. And of course, with that, we have put a lot of efforts to push the revolution and also the adoption of robotics, automation, AR, VR, and to some of a big extent, also the extended reality or XR. And of course, with that, we have the big data and AI. So what are we going to expect when we move from Industry 4.0 to 5.0? So there are a few nice features when we look at Industry 5.0 as published by EU, which is actually, we are at the center of the Europe. So the first part is actually very interesting. It's actually return of the manpower to the factory floor or return of people into the operations. And then the second part is actually the hyper customization or hyper personalization. So we are starting to put more emphasis on people, on each individual persons in the whole operation processes. And of course, distributed production, especially in the dense urban environments such as where I am from in Singapore, will become even more important and also relevant. And certainly the intelligent supply chains and also the circular and sustainable manufacturing will become more and more important. So with that, if we look at some of the enabling technologies for Industry 5.0 to happen, we can see a few highlighted themes as the enablers, such as the human-machine interaction on a real-time basis, and also the digital twins to support the real-time optimization and simulation so that we know what is happening on the real time from the different sites and also the different entities. And with that, of course, we will have to operate with the cybersecurity and also for cyber safe data management, data storage, and so on. And energy efficiency, sustainability will become an even more pressing need for us to address. So with that, we have to emphasize also the industrial transformation or Industry 5.0 is not just restricted to manufacturing, and it is pervasive for all the different sectors or the industry verticals. So how would 6G play a role in this transformation? We start to look back at our field of the IMT 2030 vision. And for that, we are referring to the vision paper development in ITU. And then we can look at these 5 different perspectives as defined and discussed in the IMT 2030 vision paper. Interestingly, they started looking at the goals and also the expected impacts. So with that, we can see human centricity becomes more and more important and more emphasized. And social, environmental, and also economic sustainability, resilience, and also sovereignty is becoming critical. So with that, we look at, what will be the users to serve when we move to 6G and also when we move to also the Industry 5.0. Then in addition to the humans, machines will be a dominant user. And also organizations from both the public and private sectors, as well as the communities will have to be the centric service that the 6G will have to provide. And of course, the different use cases and the usages will have to be included when we add the machines, communities, societies into the services. And certainly, technological enablers will be what we are after and what we are hoping to contribute through our research and innovation. And with that, we will have to define the KPIs, the performance metrics, and then the enablers. And again, if you look at, a further delve into the details, can see we have to enhance the human communications, but at the same time, enhance the machine type communications with the different metrics and enabling new services, and also push for the network evolution. Of course, these are the things that we feel excited with because this is where we are able to contribute. And then if you look at the different details, then it is converging to the summary at the right-hand side of the page, which is for 6G that we will have to push for further convergence of the 3 worlds, the human, the physical, and the virtual worlds, so that we are able to enable immersive multimedia and also multisensory communications and offer the contiguous and also pervasive and ubiquitous connectivity. And supported by the ubiquitous computing, we are able to offer this ubiquitous intelligence. And of course, with that, we hope we are able to achieve the targeted performance and also the services we offer to the users, to the community, and also the society. So this has motivated us to look at, what will be the new key performance metrics that we will have to add on when we work from 5G to 6G, and also what will be the new enabling technologies that we will have to research on. So looking at the key performance metrics, we feel on top of the EMBB or the high data rate, the URLC, the reliability latency, and also the massive MTC, which is emphasizing on the massive connectivity. We will need to also add in the key performance metrics related to synchronization of the network entities or the endpoints, the availability of the connectivity, as well as the resiliency of the network. So with that, we have to work on quite a number of enabling technologies, as also shown in yesterday's keynotes. For example, I think yesterday's second keynote was talking about ICAS, or integrated communication sensing, and also the optical wireless communications. But here we think, in addition to that, we have to further push the software-defined softwareization, or software-defined everything. And we are going to share a little bit more detail on what we mean by SDX, or software-defined everything. And of course, when we have to enable the ubiquitous intelligence and ubiquitous computing, the privacy preservation and trust will have to be integrated in the network design from the different layers. And certainly, the in-system and also the in-network AI and machine learning will have to be designed from the beginning of the specification. We have been emphasizing the key performance metric of network synchronization, and that has to be extended to the wireless endpoints. And for that, we put it as wireless time-sensitive networks. And certainly for the sustainability, it will have to extend to both the network and the devices. And for that, are we able to push our innovation to achieve a net zero devices and also net zero networks here? And of course, to achieve the networks availability and also resiliency, we will have to push the fabric of networks to integrate the terrestrial based in non-terrestrial networks, and also to look at both the user-centric network and also the digital twin networks, so that we are able to support the Industry 5.0 transformation, but beyond Industry 5.0 transformation as well. So with that, I would like to also show a very quick example to make a relevance from where I am coming from. That is a use case in Singapore's maritime and port applications. I start with actually the ambitious goal set for the 5G network in the maritime and port. And as you can see, there are in total 10 use cases ranging from the support of autonomous vessels, autonomous guided vehicles, AR, VR, remote handling of the vehicles, remote, and also predictive maintenance and so on, so as to push for the enhanced safety, efficiency, intelligent system fully integrated into the operations, service continuity, seamless connectivity, and so on. So what would be the problem? That we will not be able to fully realize this dream by just using 5G. The problem is really lying in a few folds of aspects. The first one is actually the challenging wireless environment in such an operation. Why so? Because it is a busy operation with stacks of containers having metallic architectures. And of course, with that, we are facing a very hostile wireless propagation. And to add it to an even more challenging scenario, the containers are continuously moving. And then we are going to have dynamically changing wireless channels and blocking our signals. And of course, with these 10 different use cases, we are expecting also the URLLC, the high data rate, high capacity, and also covering both the port and the water, as well as the air, because we are also making use of drones for the different services. So with that, it is really a matter of having the pervasive and also massive connectivity at both the port and the sea, and also to support this high data rate and also high network capacity, and with the URLC, as well as the high precision localization. And obviously, through the trials, we have been seeing a lot of challenges for 5G to realize all this vision. And to add it to the further challenge, we are targeting to increase the number of deployed automated guided vehicles, or the AGVs, that are carrying the containers from one terminal to another. and also to increase the number of the operations that are remotely managed by digital twin. So with that, really the 5G part, even the wireless time synchronization is still lagging behind. And let alone, the pervasive connectivity to cover the sea and also the port in such a, dynamically challenging and also hostile environment. So this is really motivating us to look at, what are we able to offer if we move from 5G to 6G? And then the second example I'd like to share, which is related to the keynote just now, but looking from a different perspective. I think we have been motivated from the keynote just now that mobility as a service, electrified, will be a sustainable operation model for our next generation of the mobility. And then if we look at it, and then for 5G, we have already defined the performance and also to serve this smart grid with the URLC and also with the deep link budget support. However, when we move further to the more sustainability models and also the even massive electrification for the vehicles, then we are seeing higher challenges to come in our way. Because all the renewable energy resources, for example, the solar panel will have to be monitored. All the electrical vehicles will have to be monitored as a distributed energy resources, or in the renewable energies terminologies, the DERs. And then of course, the monitoring will also add in a lot of behind meter assets for us to connect with, for us to monitor and compute and then control. And to control all these as a distributed energy resource, we will have to synchronize them with tight synchronization performance requirement. And certainly to serve all these electrified vehicles assets, we will have to also manage the charging facilities and optimize the charging facilities so that we are able to support the energy transaction as well. And of course, for the transaction, we are not only having, the short package, the digital ledger management perspective, but also the URLC perspectives too. So looking at this requirement, we feel indeed we will have to add on top of the URLC, the massive connectivity with the URLC features, with the URLC KPIs. And certainly to control all these distributed assets, we will have to also synchronize them tightly with the specification that we are going to share quickly. So to summarize the discussions and also with the examples that we have shared, we feel there are 5 aspects we will need to work on. And the first one is to serve the machine as a dominant user. And then the second aspect is to have this agile and software-defined everything. And then the third one is to have the privacy, security, and resilience as a warranty when we design the 6G network. And certainly the sustainable networking and also the energy efficiency will have to be designed as a baseline. And last but not least, for AI to play an active role to incorporate AI natively in the system and also in the network. So of course, if you look at another level of detail for all these 5 different aspects, we have a few technical items to push forward to, as I have given here. But with the interest of time, I'm going to quickly just share a few ongoing work to seek your comments and inputs, and of course, also seek collaboration with you as well. And then the first one, of course, is for the machine as a dominant user. We are particularly looking at the integrated communication and sensing, and with the joint radar communication as a special example. And certainly we are also looking at how are we able to synchronize the different wireless endpoints with this high precision and common clock reference for all these wireless devices. And then the second aspect for the software-defined everything, of course, we have software-defined radio network, as well as the environment supported by the active intelligence service, but at the same time, looking forward to 6G, we are still seeing a high relevance of the spectrum segmentation. So how are we able to design our systems and also the devices with a much more efficient architecture so that we can have this flexible carrier aggregation or spectrum aggregation? And certainly, how are we able to embrace AI and also the deep learning models in the systems and also in the networks so that we are able to further push the performance? So I'm going to quickly share some of the works that we've been doing. And first, the integrated communication and sensing, or ICAS. I think we have heard quite a bit from yesterday's presentation already in the keynote session. But just to recap, we are looking at how are we able to make use of one single system and one single spectrum to enable multiple functions. And with that, certainly we hope we are able to serve different application scenarios with a much more efficient hardware system and also a much more efficient spectrum utilization. And certainly there are going to be a lot of use cases. And for here, I am sharing in the industry 5.0 or industrial operations. And hence you can see that I'm giving these autonomous systems of the AGVs, forklifts, as well as the presence of the human user coexisting in the same, for example, factory floor. And so how are we motivating the use case? Because while we send the communication signals across the different entities, we hope we are also able to make use of the reflected signals from the different objects, different humans, so that we are able to detect the presence, estimate the speed, and at the same time, estimate the range so that we are able to manage the safety and also avoid the collision of the different objects. So of course, with this, we do share a number of hardware components and blocks through this integrated joint radar communication system design. And certainly there are different options. I think that has also been shared in yesterday's presentation already, that we can make use of the comms waveform to enable the radar sensing capability. And the second, of course, is if we have the radar systems in place, how are we able to embed some of the communication systems signals so that we are able to have better communication and also better knowledge sharing? And the third option will be each of these two functions will still use their own waveform that has been optimized for its own purpose, but we can time share or we can power share them. And last but not least, are we able to design a joint radar communication optimal waveform? So of course, if you look at the performance, we will have to satisfy the performance of both the communications and also the radar sensing. And with that, given the nature of these safety critical operations, we will have to also put in place the anti-jamming and also the anti-spoofing feature in the design as well. So are we able to achieve the performance requirement at all? If we look at using, for example, the comm signals to support the radar sensing capability. And shared here in this page is actually one case study that we have made a few years back. And that is the time we were looking at this 802.11 AD Wi-Fi signal at the millimeter wave band 60 gigahertz spectrum, which has also about 2 gigahertz bandwidth. So you can see that we are really trying to make use of this wide band signal to enable the radar sensing capability at the same time enjoying the gigabits per second data rate transmission. So interestingly, through designed the so-called FCCR or the fast cyclic correlation radar algorithms, we are able to achieve by dual using this 11 AD signal, the radar sensing performance of sub-meter per second of speed estimation and also about centimeter level of ranging accuracy. So it is indeed very encouraging. to reuse the COM signals to achieve this very high performance of radar sensing capability. And of course, if you look at it and also look at reusing the 5G signals, there are some challenges for us to address if we want to push similar level of performance, especially at the C-band, because we are having a much narrower bandwidth of about 100 megahertz only to work around with. And for the millimeter wave bands, of course, it's a different story. So a little bit more detail about this FCCR or the fast cyclic correlation radar algorithms. We are really looking at, what will be the COM signals that we are able to tap on so that we are able to, push for this dual function of radar sensing. And so how does it compare with the traditional OFDM radar algorithms? And certainly we want to show, the advantages so that we are able to brag. And so in terms of the complexity at the rightmost column, these two designs share the same level of complexity, but if you look at the robustness and also the flexibility of dealing with different commonly used communication waveforms, we can see the FCCR does give us this flexibility to work with different, cyclic prefix single carrier or OFDM or zero prefix unique word prefix, those circularly stationary signals. So with that, of course, we still have a lot of challenges to overcome. As I mentioned just now, if we look at reusing the C-band, which has a much narrower bandwidth to achieve a similar level of radar sensing capability, what can we, further push the performance? How are we able to tap on the additional dimension of the multiple antennas to help us? And of course, the radio design itself, because of the nature of a full duplex system, and also the multi-user interference, the multi-radar comms device interference, will be still a lot of challenges for us to move ahead. And certainly, if we want to enable this function, we will have to make sure the standard, the protocol cycles allows us to share some of the signals, some of the information between the base station and the device, and also hopefully among the devices to share the sensing information as well. So anti-jamming and protocol design will still be some of the additional work for us to even enable this function in the beyond 5G system. And last but not least, are we able to have a optimal waveform that is able to support both the optimal sensing and also optimal communication? There have been a lot of discussions, about OTFS. Recently, there have also been these discussions on the ODDM, or the orthogonal delayed Doppler modulation. So I think there are a lot of, good features about these two waveforms. However, the challenge is still, related to the complexity. If you look at OFDM systems, really we have very nice, simple structures at both the transmitter and the receiver. And when we extend to the multiple antenna system, there are also a very natural extension without too much of additional complexity. But the challenge for us to really address when we look at OTFS or ODDM is the extension of the multiple antenna capability with managed complexity. So there are still a lot of work for us to address these challenges. Next, I'm going to quickly share, what do we mean by this time synchronization among the wireless and nodes? By this wireless time sensitive network. It came from the 802.1, the time sensitive network standardization, but really it will go beyond that for us to work on. As a quick recap, it really is motivated from the perspective of supporting by the communication network of the multiple control systems so that we have the capability of supporting these different traffic classes. And these different traffic classes may have different cycle times. And also, with this low latency transmission requirement and also the low jitter, so that we have a very tight synchronization, a common clock reference. And then if we look at quick summary of this, we are looking at deterministic network, that we have to transfer the packets within the deterministic window. And at the same time, each of these network points will have to have a common reference of clock. And this common reference clock will have to be there all the time. So the tolerance of the jitter or the correction of the jitter will have to be in place as well. And then with that, another aspect is actually the resource management. With or without the network traffic or the congestion, the performance will have to be consistent. So to enable this, we have a few or 4 features to satisfy. The timing, the synchronization aspect, of course, but at the same time, the bounded low latency and the ultra reliability. Of course, these are connected together. And these features, these 3 features will have to be there and guaranteed even in the presence of the network congestion. So the resource management, scheduling, and the prioritization will be also critical in the wireless time-sensitive network design. What I'm showing here with these 2 curves are just a simple indication that it is possible when we look at, the simple network scenario, that we have only this single class of traffic, predictable, cyclic. So we can actually, depending on how many users we want to share in this local area, we can achieve different level of latency requirements. However, the challenge when we move ahead, of course, here we are also showing, this is not only just about the simulation and performance analysis. The performance analysis and also the simulation results can be ported over to the hardware systems without much of performance degradation. However, the challenge is really is when we move to the multiple traffic classes of support in the single network. And also if these multiple, even the cyclic traffics will have different cycle times. And also how are we going to design the whole system, with cost-effective protocol and cost-effective time stamping in the hardware design. So these will be still some of the further challenges for us to address and moving ahead. And certainly the design I'm showing here is based on a modified protocol that we will have to do regular carrier sensing or the network sensing. But to move ahead with the 5G or 6G network, the protocol aspect in terms of the overhead of the time stamping will still be maybe still a big challenge for us to work toward. Certainly, I will look forward to your comments and feedbacks to see how we are able to address this together. So next, I will quickly share, the other aspect, which is related to the software-defined everything. We have been working over the years, starting from software-defined radio, and then we moved to cognitive radio so that the software-defined radio will have some level of intelligence. And then from the network community, we have also the software-defined network. And then the last few years, we started to see, software-defined wireless environment that is supported by this RIS or the intelligent services. And so how are we motivating us to look at, our unique angle of contribution? Again, we are looking at, the spectrum segregation perspective and also the spectrum scarcity. And with that, we are now able to get away, even we move from 5G to 6G, that we will have to address this spectrum segregation and aggregation so that we are able to utilize the spectrums more efficiently. So with that, the issue is really lying on the hardware complexity, which we hope we are able to address. And that can be seen as this simple illustration. traditionally, when we design the system, whenever we add in one more carrier frequency to support in the system, we will have to add in one chain of the RF and also the mixed signal arms, so that we are able to convert the signals between the digital domain and the RF domain. And really, when we have a lot of different non-contiguous spectrums to aggregate to support in the system, we are seeing the potential of stacking up a lot of parallel chains of these filter banks and also the power amplifiers and the antennas. Are we able to simplify through the signal processing perspective, simplify this overall system architecture from this multiple chain of the RF and the mixed signal design to a single chain, as we are illustrating from the right-hand side of the figure. And of course, to do that, we will have to look at, what will be the signal processing perspective that we have to tap on and also optimize. And for that, we are looking at the compressive sensing and the sub-Nyquist sampling perspective to optimize the whole design. And of course, with that, hopefully we are able to realize this, unified but multiple spectrum aggregation perspective in a simple circuit. And of course, with that, if this is truly possible, what we are hoping to achieve further will be through the single chain of the RF circuit and the mixed signal circuit, are we able to reconfigure on the fly depending on which spectrum are available for us to aggregate with, and then we are able to reconfigure, and then that is giving us really the software-defined feature in the system design. And through the analysis and also the design optimization, we are seeing a very encouraging results as what I'm put on this page, that this single chain of RF circuit design is possible. And also we are able to reconfigure, the component carriers for us to aggregate with using this single chain of the low complexity architecture. And to prove that, I'm also showing that, with this hardware prototype we have developed in the lab, we can aggregate these two bands over the 5G new radio spectrum and the waveforms. And you can see the decoded constellations from these two arms of the spectrum that we have aggregated with at the base station processing. And certainly, this is a new architecture. We are introducing some of these nonlinear behaviors as well into the whole system. And if we follow the traditional approach, we will have to look at what will be the nonlinearity like, how do we model it, and then accordingly, we are going to mitigate these nonlinearities through different design approaches. So now with this, ubiquitous intelligence that we have, and also we are able to embrace with, we are also looking at maybe we can, do away with the attempt of developing a model for the nonlinearities, but we just show the signals into a learning unit of this RNN architecture. And with that, we can see the performance enhancement as we have, tapped on the hardware prototype we have developed using just a long short-term memory architecture. We are able to push for the error vector magnitude enhancement by about 8 dB when we have these 64 QAM signals in the two arms. And at the same time, this implementation of the LSTM into the hardware chain of the receiver, we are still able to meet the latency requirement for the receiver processing. So I think this is encouraging on one hand, but at the same time, we are also trying to ask and also trying to profile what is going to be the power consumption of this animal even though it is a lower complexity unit. And so eventually, are we going to embrace such a structure at the receiver, at the base station, or are we still going back after we learn more about the nonlinearity and then have a lower complexity architecture through a model-based approach? So this is still an open-ended question for us to further work on. And of course, this is only the physical layer demonstration, as I showed in the previous page. We are keen to look at also the integration of this new architecture with the protocol stack and also with the core network, so that we are able to support the end-to-end performance integration. And indeed, this is possible by embracing, for example, the open layer interface and also the open 5G core network from the open network community. And we are able to integrate the whole design from the hardware, from the new, even though it looks messy, of the RF unit to support this end-to-end, Zoom calls by the different 5G modems. And certainly, we still have a lot to do to further push this piece of the work. How are we able to, move the technology readiness level so that we are able to be more robust to the interference when we aggregate the different, component carriers, and also the support of the multiple radio access technologies, because after you aggregate the signals at the receiver, really the protocol stack will be actually independent of the signals already. The support of the multiple access shouldn't be a big issue. However, we still need to work out the details. And certainly, how are we able to integrate this design with the, the big concept of the software-defined network, the environment in a unified approach? I think this will be still a lot of work for us to push forward to. And certainly, we are not able to forget about, this hot topic of AI and deep learning, and how are we able to embrace it so that we are able to further push the performance boundary, and at the same time bear in mind, the energy consumption and also the certain sustainability perspective. And putting it into a real-time operation, we will have to know how it is being implemented, how it is bounded, so that we are able to control it, and also make the network manageable without ending into a catastrophic scenario, and also the standardization perspective as well. And certainly, I think we are going to hear a lot more about, semantic communications and also the foundation models. How are we going to embrace it so as to push the performance boundary in the network? But again, another perspective is, when we look at the efficiency and also the adaptability, it really involves the different points at the network, from the cloud, from the infrastructure, and at the same time also the different devices, so that we are able to have this distributed, centralized, and also the collective intelligence and collective learning to embrace the transferability, adaptability, and support the personalization of this intelligence, protect the privacy in a cost-effective manner. And again, I want to quote, it is actually helpful for us. It's just a matter of how are we going to embrace it in the architecture efficient and also cost efficient manner. And also, when we move forward, are we still going to, rely on this black box learning, or are we able to derive the model through this learning process so that we are able to go back to a more efficient model-based approach? And certainly, a lot of work also in the hardware perspective. And in the interest of time, I'm not going to the details. This is about, addressing the power amplifier efficiency using this deep learning model. And really the objective is for us to push the power amplifier operation efficiency by this enhancement of the linearity And at the same time, how much more power consumption are we introducing to the system will still be an open question for us to address. So finally, I think this is a very exciting time for the community. We hope we are able to work together, receive your comments, and also collaborate with you. And for that, I would like to share some of the research student attachment models and the support we are able to put forward from A-Star, from my organization, to support senior undergraduate master students as well as PhD students. So with that, we look forward to work with you. And also, if you are interested in these schemes, please discuss with our supervisor and feel free to contact me. Thank you so much.
Thank you so much, Sumei. So I learned so much about Industry 5.0. Maybe we have time just for one quick sharp question before we break for coffee. Oh, Professor Adachi, thank you. You give me a bit of exercise as well.
Thank you very much, Sumei-san. I'm very much interested in software-defined spectrum aggregation. You talked about 3.6 gigahertz and 5.2 gigahertz only. But currently, millimeter wave is going to be deployed, but not so successful right now. But still, the sub-6 frequency band is very much useful. So in the near future, we have to simultaneously use both 28 gigahertz and sub-6 at the same time anyway, because of the propagation difference is so huge. So can we apply this technology to accommodate? But difference is so huge.
Yes.
What do you think about this spectrum aggregation?
Right. A very quick answer will be it is possible to aggregate even if they are spaced quite far apart. We are able to handle it from the RF circuit perspective. And then another aspect is also, if they are fixed, we don't have to reconfigure them. Then it is maybe not necessary for us to put into this architecture. It's really those that we will have to reconfigure very frequently. Then we can tap on this architecture. It hopefully is able to give us more benefits. I think.
Indeed, there's always a lot of funding required to make a vision reality in terms of hardware. So that's great. So yes, I just have two quick announcements to make, and then we will break for coffee. So the first one is that right after the coffee, we have a wireless futures panel, and this will really host the